PCA, and then how to interpret the root
Like
mean.
you go to hospital now, why you okay?
The root
Uh-huh.
SE will interpret the root SE, and then we'll transform the data. We'll have to take the negative side of it too, and then we'll deal with regression diagnostics, and then we'll pack a bit. So please bear with me as we go along. Please bear with me as we go along. All right. So last lecture we talked about we extensively talk on the correlation analysis, and then we also talk about multicollinearity in the data and how multicollinearity can be resolved in the data. We talked about that very well extensively. But today, I will take us to diagnostics, regression diagnostics. Sometimes you run your regression analysis, and then you have to check whether what you run it's actually right. Are your hypotheses okay? Are your results okay? And that last lecture we talked about the composition of variation. We talked about the goodness of fit, and then we talked extensively on the R-square. Yeah, a little note here. R-square tells us the total number of variation explained by the regressor or the independent variable. The R-square talked about or tells us the total number of variation explained by the regressor or the independent variable. And then we also talk about the adjusted R-square. The adjusted R-square, this tells us after adjusting for the number of regressors, after you've adjusted for the number of regressors in the regression analysis, the total number of variation the model explained. You can see that if we do some adjustment in our regressors, the result will be the adjusted R-square. That result tells us the total number of variation after the adjustment. Now, someone asks of what is the meaning of the root mean squared error. The root mean square error. This stands for the standard deviation of the residual. This shows that the average size of the prediction error in the unit of the dependent variable, the root mean square error tells us the average size of the prediction. Like when we forecast, we run an analysis, we get a result or the regressors, how the regressors are predicting the dependent variable. So the RMES tells us exactly the average size of the prediction error in the unit of the dependent variable. Now, when you run the result and then you realize that your root MSE is low, it's low, or let's say it's small, less than 10%, less than 5%. The average is less, let's say it's less than 0.500, shows that the lower value indicates better fit. When the square error mean is low, it shows that indicate that the whole result is better fit or is better well situated, or the prediction is accurate. But interpretation depends on that. When the lowness of it, the interpretation depends on the scale of the dependent variable. When we talk of the scale of the dependent variable, like especially those who go for primary data, you know how the scale mean or the predicted variable, how it look like. So your interpretation depends on it. So you can have a low root mean square error. You might not interpret it well, but it might have a high one too. You can interpret it well. But the low one, that is below 50%, is low, indicates that the model is fit properly. So that was last lecture. Today lecture, we are going to regression diagnostics. Regression diagnostics. The question is, somebody asked, why do you have to perform diagnostics for our regression? Why do you have to perform diagnosis for our regression? After going to the hospital and then you receive treatment, you have to go for review. You have to go for review and check whether the treatment given to you, it's accurate, it's proper, whatever. So you perform diagnosis. Regression diagnosis are tests you run after estimating a regression to check whether your model satisfies key assumptions. Normally, the key assumptions are the hypotheses that we talk about. The key assumptions are the hypotheses we talk about. So after you run your regression, you check whether your model that you've run or the analysis that you've done is satisfied the key assumption. If this assumption fail, your result may be biased, inefficient, or misleading. So it's not just enough running regression analysis that I run regression and then the beta square p is like this. No, you need to check whether it is actually okay. Now, there are some way you check. The first one is you check for multicollinearity by performing the VIF test. The VIF test. The question is, what is VIF? That is variance inflation factor. So when you run your analysis, it's important to perform variance inflation factor. It's a statistical measure used in regression analysis to detect for multicollinearity. That is whether independent variables are highly correlated with each other. The last time we talked about multicollinearity, and then we are saying here that if you want to perform diagnostics of your estimation or your analysis, you need to perform the variance inflation factor. It is to check whether the independent variables are highly correlated with each other. So mostly or importantly, when you perform your correlation analysis, you can actually determine whether your regression will be fit. So someone asked a question last time, is he a mandate? Is he asking for us to perform correlation analysis? Now, I can answer that question straight here by telling you that because of the result regression diagnostic, it is important we perform that aspect. The VIF measure how much variance or uncertainty or a regression coefficient is inflated due to multicollinearity. So it is important to perform it. Here, when you're performing the regression diagnostics, if you check your R-square is obtained by regressing one independent variable on other variable, and if the R-square is higher, it leads the VIF become larger. When you run your analysis, you notice that your R-square is higher, your VIF become larger, and then there's definitely multicollinearity problem. That there is multi over there. Sometimes you run your regression, you realize that you are 98, like 0.98. Yeah, they are high. Then there's possibility that there is a multicollinearity problem. Some of you can run your regression and realize that the R-square is very high. And you say, oh, yes, very good R-square, very good R-square. Mind you, there is a problem of multicollinearity. It will definitely lead to the VIF being large. Now, the boundary or the yardstick, the rule of thumb is that when the VIF is less than 5, there is no problem. That means that it's less than 0.05. If the VIF is less than 0.05, there is no problem. That means the 5 years is the 5%. But if it ranges between 5 to 10, right? that there's a moderate concern. If you read it from 0.0, if from 0.01 or 0.055, 0.01, then there is no problem. But if it's above 10, then there is a serious problem. If it's above 10, there is a serious problem of multicollinearity. The VIF will happen. Now, what do you do if you have a VIF high? One, draw one of the correlated variables, combine variable into an index, use PCA or keep variable if theory strongly justify them. The last time we had a lecture, I told you that, or I explained to you that if you notice that there's multicollinearity in one part between one particular variable, first of all, you also have to go and check theory. If theory actually supports that, and I made a right example that mostly when you are doing correlation between import and export, tendency of multicollinearity occurring. There is always a tendency of multicollinearity occurring. And so when you do that, quickly just have to go and check theories or literature to support it. Then there's if literature or theory support it, there is no need to worry. Now, another way to do or checking for diagnostics is heteroskedasticity. Heteroskedasticity. This one occurs in regression analysis when the variance of the error term, that is residual, is not constant across observation. It occurs in regression analysis when the variance of the error term, the residual, the mu, when you write your equation, you definitely put the error term in it. That is what the error term, the last members of the equation of your model set is the error term. It said that it occurs in the regression analysis when the variance of the error term is not constant across observations. You see, regressor or error changes with the level of an independent variable or fitted variable. Sometimes when you begin to add more of the independent variable, like the multiple regression, more, there is a tendency of heteroskedasticity in the result. Now, the boundary says that when it's less than 0.05, then that hetero is present. So when it's greater than 0.05, no problem of hetero. Why do you think heteroskedasticity is a problem? One, incorrect standard error. The problem of hetero is that it leads to incorrect standard error. It also leads to invalid t-statistics and p-value, and also misleading conclusion about significance. So the problem of hetero means that, one, there will be incorrect standard error, there will be invalid t-statistic or p-value, and they will also mislead conclusion about significance. So these things you need to perform to check if your model that you set, the analysis that you perform, the regression that you perform, the prediction, the forecast, whatever you call it, estimate that you perform are okay. You need to check for heteroskedasticity in the world. Now, another thing you should also check for, or some of the tests that you can perform, is normality of residual. Normality of residual. Normality of residual means that the error term residual in a regression model are normally distributed. Normality of the residual means that it means that the error term or the residual in the regression model are normally distributed. That is, they follow a bell-shaped curve. They follow a bell-shaped curve. Yeah, like a bell shape. Like you see a pregnant woman, how the pregnant woman stomach look like, and that one. But if it's flat, it's not a flat one we're talking about, with a protruded one and a bell shape. Yeah. What did I have to use a pregnant woman as an example?
Nice one.
Anyway, So that is that. So we can also see the yardstick here, the criteria here for the normality of residual. You can see the criteria here. The p-value can be used as a yardstick. The p-value are mostly used as yardstick to check it. Okay. Note, in a large sample, I want you to take pay attention to this. In a large sample, normality is less critical. In a large sample, normality is less critical. But with a few sample, yeah, the opposite of this. The few sample, opposite of this. So, and it's important that when we are doing diagnostics, we are doing diagnostics, we need to first check for normality, heteroscedasticity, VIF. Now, why do we need? Why is it that the normality matter? Does it matter? Someone is saying, okay, my regression, my analysis, it's okay. I have my beta. Some worry, some people actually have the answers in their pocket. So when you fall on it, who you are, we are okay. Okay. Now, but why do you have to go and check for that? Normality is important for valid hypothesis test. So another way you can check if the hypothesis are actually fit or your conclusion on your hypothesis are actually fit is to perform normality test. You see, a valid, reliable confidence interval. Why do we have to perform it? For us to be sure of reliable confidence interval. Note, a large sample normally is less critical. That's the central limit, the theory over, there's a theory supporting it. Okay. Now, some of the things we can perform under the normality here is the histogram. The histogram is the histogram that actually bring the bell shape. You see, the histogram bring the bell shape. When you perform the histogram in the STATA, it will bring the bell shape. Now, the bell shape, when it comes, that means that it's good. But when it's skewed or it's flat, when it's skewed or it's flat, then there is a problem. So it's important we take that. Now, somebody may ask, now, what actually, if you run it, what is causing that? What caused normality? What caused non-normal residual? We have something we call outlier, skew data, model misspecification. The most important here is that model misspecification. Now, you see, I write models, right? I write models. And I know that there are some people, they misspecify the models. Now, let's assume this. Let's assume this. Let's assume that a human being is walking. Okay. What is causing the human being to walk? With the aid of just the normal human being. We say it is walking with the leg. So the leg is contributing to the human being's walking. Right? The leg is contributing to the human being's walking. Now, that is say we can say that the legs contribute to the movement, effective movement of the human being. That is accurate. Now, but if I come to say that the one leg and one arm contribute to the human being walking, that is misplaced. Are we together? That is totally misplaced. Specified model. The leg perform a different function. The arms also perform a different function. Okay, it's misplaced. Sometimes let's take this basic economic problem. One of the basic economic problems. You say that yes, one of the misplaced model, like the law of demand, basic law of demand, that says that when the price is high, consumers buy what? Less. Okay, but when the price is low, consumers buy what? More. Now, how do we misplace this model? Let's take the model that we are selling pork. Okay, we are selling pork, and our target market is what? Is the Muslim community. You see, and then you you go to the emotionless community with the pork and saying that the ability of you getting more income is selling pork at emotional community. It is totally misplaced, right? So sometimes we specify our model. It's a good model, but we misplace the model. So this occurs when we misspecify the model. Are we together with the little example that I'm giving? Oh, this man is just talking too much. Okay. I'm not talking too much. All right, so let's go on. I feel alone in the class. Yes. Mr. Edu. Mr. Edu. Okay. Let's go. Now, what to do when you have that problem? Number one, transform the data, which we will definitely do today. We'll transform the data or remove or investigate the outliers. Use robust model. Yes, use robust model or improve model specification. Check your model. Check your model. Check your model. So it's important when you are working, you need to check your model. Now, let's do a quick recap, a quick summary of this whole thing. Now, the quick summary means when you want to do diagnostics. Now, first one, we check residual error from regression. Normality, a bell-shaped distribution. We should have that. And then why is it important to value T and the F statistic? You see, and we can perform this particular command histogram from command in the STATA to get it done. Now, some model specification. So the model specification error, it occurs when we have the p-value. When the p-value, one is greater, one is less, then we have a problem. Okay, so with this threshold, this count point, a higher p-value or lower p-value, the reverse of the specification is what we see. Sometimes we can perform another analysis or diagnostics by doing the Durbin-Watson text. I have a paper published already on Durbin-Watson. Okay, I'll along the line, I'll show it to you. We have to perform this test to check if we have any problem in our analysis. So in general, to diagnose your regression, the good results are one, check for multicollinearity with the VRF, heteroscedasticity with this, and then normality, and then specification, autocorrelation. So from these parts, these are the threshold or the cut point to check for all your diagnostics. Any question before we go to the practical? Any question? Today, few people in my class. I can only see. Mr. Collins, any question?
I think I'm okay.
Okay, all right. What about Madam Francisca? Madam Francisca. Madam Francisca logged in, is not in the class. Okay. Mr. Tutu. Osei Tutu.
Yes, Doc. Yeah. In fact, I'm really appreciating the lessons. I'm okay.
All right. Thank you. Thank you. Okay, Mr. Johnson is in the class. Senior man, any contribution? Mr. Johnson.
Doc, thank you. Oh, thank you, Doc. Oh, your boy is listening. Thank you so much. Thank you.
All right. All right. So, okay. So, okay, I will not disturb Molly. Molly is in the class as well. All right. So let's try and perform some of the analysis, some of the work here. Some of the work here. So please, if you have your STATA ready, launch it. Launch it. Launch your STATA, and then we take it from there. Okay, so now, first of all, let's perform the PCA first. The PCA, it's simply one of the analysis that we actually use as we discussed the last time. The PCA is one of the analysis we use as we discussed last time. The PCA corrects multicollinearity in the data. The PCA corrects the multicollinearity in the data. So let's perform a common correlation analysis, and then we check that, and then we check that. I'll call a different data, but okay, let's use the same data. Let's use the same data. Let's use the same data. And it's just for us to check something. All right. Okay, so the data is called into it. Let's set it on time. Let's set the time value. Let's set the time value. So the command for setting time is tset year. And then you click enter. Our time variable is set properly. Our time variable is set. Now, if our time variable is set, let's perform a simple correlation analysis as we did the last time. Statistics, summary and descriptive, and then you just come to perform a simple correlation analysis here. And I quickly call in the variables. You call in the variable you TFP, GDP growth, export, import, net export, inflation, infrastructure, education. And then we just click OK. And the last time we performed the analysis, we noticed that there is a problem of multicollinearity here because the threshold is any figure above 0.8, there is a serious problem of multicollinearity. And we can see from this issue here that there is, because from import to export here, there is a problem here. Now, how do we correct this? We first of all say we can check theory, we can draw, and the PCA correct it for us. Now, it's a step by step. Now, the first thing we do is that we go to statistics. So follow me as we do. I'll any step I go to statistics. With a drop down, come to multivariate analysis. And then you see the arrow point over here. Okay. Then you come to factor and principal component analysis. Statistics, multivariate analysis, factor and principal component analysis. Then you come to principal component analysis, PCA. We are not interested in the covariant matrix. We are not interested in the correlation or whatever. We are just interested in the PCA to correct the problem. We click it. Now, after clicking it, you call the variables that you've done the correlation analysis on. Yeah, the variable that you did the correlation analysis on, you call them. We did on TFP, GDP growth, export, import, net export, inflation, education. Okay. Now, after this, you see between and if we leave it with reporting, advanced model 2, you leave it. We are only working on the model 1. Then you accept. Now, when you accept, basically we have the corrected issue. The issue we are talking about, the PCA is already corrected with this. The principal component eigenfactors. Now, when you check here, we have component 1, component 2, component 3, 4, up to component 7. Now, the components of our variable, how many variables are we doing? We have 1, 2, 3, 4, 5, 6, 7. So the component up here is the same as the component up here. You see, now we are saying that the rule of thumb is that which of the eigenvalue, the value said that any number that is below, anything happening? Is it mine? Please, can you still see my screen?
Yes, you can see.
Yes, please.
Okay. Now, the rule here is that any number below the eigenvalue, below, right, is not accepted. Below 1 is not accepted. And already you can see that the eigenvalue here are from what? 4, 3, 4 and 1. You see, and their proportion is at 58 or 50, almost 59%. Okay. And then the difference between them, between these two variables, is 2.71713. Okay. Now, how many components are above the 1%, the 1 we are talking about here? We have 1, 2 components. Only these 2 components. You see, only these 2 components. And when you come to the cumulative proportional, cumulative effect, we can see that the first component, which is 4.116, explained up to 58%. And then the second component, which is 1.39990, explained up to what? 78. And it goes down, 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 down. You see, below the cumulative gets higher when it's below the 7. It's below the 7. Now, we can see that we have how many components? 2 components here. Basically, when we come to check the correlation here, basically we have corrected the whole thing. Now let's look at TFP, right? TFP, GDP growth, export and import. The problem we have here was what? Import having a problem here at 92%. Okay, but when we come here, components 1, 2, 3, 4. So component 1, 2, 3 is corrected to be what? This. But let's check further. Actually, it's corrected. It's corrected here, but let's check further. We can do the post-estimation, post-smoothing of it, and see how the variable spread, how the variable form the curve. Okay. Madam Maureen, you asked this question. Please, are you following?
Yes, I'm following.
Okay. All right. So we can continue to do other tests here. Then we come back to multivariate analysis. We come to this whole place, and then we have to post-estimation. Post-estimation. Let's check the post-estimation. For the post-estimation, you do, first one, you do script plot of eigenvalue. Let's check the script plot of eigenvalue. First, the reason we are checking the script plot of eigenvalue is to check these components, whether it is actually through, whether these eigenvalue are actually accurate. Then we go for the script plot. So we go to statistics, still multivariate analysis. Then we come to post-estimation. We go to script plot of eigenvalue. Now, here, a window pop up. You see the mean, CI plots, all these things. We are talking about, we want to obtain the eigenvalue from the previous estimation command. We want to check, we are using this eigenvalue of the previous estimation. So it's already here. We are not going to specify anything. So we leave it. We just only allow as it is, and then we said we agree. Now, you can see from the curve here. Let me do it side by side. You see that here we have 4.116 and then 1.399, and then it dropped from this place. You can also see from the curve here, the plot here, when it got to this place, right after 1, it dropped. So we have only 2 main components of the eigenvalue. We have 2 main components of the eigenvalue. So we accept that it's true. Now let's do another loading plot and see if it actually that is the case. Now you go back to the
please before you go there. Please.
Yes, sir.
When we go to statistics to multivariate to post estimation, which other variable, what did you select to get there?
Okay. I like the break. Break. The you see here, principal component analysis, post estimation, and then script plot.
Screen plot. Okay.
Yes, please. Then we accept the eigenvalue here. We are talking of the eigenvalue, so it's already clicked. It's already selected for us. So we don't click anything, we only accept. Okay.
Okay.
So did you also work? Now let's go to another. Let's try to see if actually works. Now
yes,
we
it
still
works.
come to.
Thank you.
Okay, we still come to the statistics, multivariate analysis, and then we still have to come to. We are still doing the post estimation, but let's do loading plots. Loading plot. So gradually you do script plot first, then you do loading plot. Now the loading plots, we have how many components are we talking about that are actually accepted here? We have only 2 components. So only 2 components are above 1. But if we have up to 4, 5 components that are above 1, fair enough. But at this point, we have only 2 components that are above that. So we accept the components here to be 2. If we have up to 4, we click they are 4, they are 3, they are whatever. But this time they are only 2 components. Okay. Now then we plot it. On the y-axis, we type component 1. On the x-axis, you also type component 2. Okay, component 2. All right, so you leave the title, you leave the overall, you leave everything. Okay, then let's accept. We accept. Then we wait for it to come. Now, look at our plot, loading plot. Our loading plot. You can see that the first component 1 and component 2 are also here. Component 1 and 2 are also here. So basically, the most important part of the whole PCA, we did it already, but we're only just trying to see how the variable works. But you see, importantly, surprisingly, when you go to data view.
Hello, sir.
Yes, please.
Before you go to the data view, on the loading plot, please, can you give a recap of what you did there to
get to the loading plot?
When that interface displays at the title, you said you type component 1
and component at the y-axis component 1 and the x-axis component 1, component 2.
Okay, so for mine, I can see. Okay,
I'm doing it. I'm doing it again.
All right, sir.
All right, so multivariate, right?
Yes, sir.
Then we come to the factor, and then we come to post estimation. We come to loading plot.
Okay.
And we come to the y-axis component 1, x-axis component 2.
Okay.
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 And then we accept.
Okay.
You can see the component 1 here and then component 2 here. So our plot.
Okay.
This is our plot. Ladies and gentlemen, the most important thing we are looking for is the components of our differences here. Okay, because the data, the multicollinearity issue in the data is not that much. It's not a problem because a theory supports mine. You see, if were to be a different data, we would have seen unexplained some percentage here, right? Would have seen some percentage here. It's not 0.0000. Would have seen some percentage here. Okay, would have seen some percentage here. So basically, you yourself, when you perform it, you can check it. You can check it yourself. Okay, but the most important thing here is that our component is explained here. Then there is no issue of multicollinearity here. So we now have minus 0.22222. Okay, and 0.222. You can see here, but we are not interested in here. We are only interested in the issue here, the issue we had here. The issue we had here. We want to correct it. Okay. Please, you can come in. Mr. Isaac, you can say something.
Yeah, Doc, thank you. When you look at the PCA we just ran, before then, the value that we were looking at, it was between the import and the export, which had issue of coloniality because it had a value of 0.92 or let's say 92%, right? But when you run the PCA, we had a value of minus 0.2222. So how do you explain the minus? Like it has moved from positive which was like 92% to now it is now minus. So to the layman, how would you explain to that person to understand? Thank you.
So it's very good you ask this question. I will basically explain it to you in a economic simple term. When your exports are more than your imports, what do you get? You get negative net export, right? You get negative net export. So you can say here in a layman term that I'm using the economic issue here, okay? That the import outweigh the export in this angle, okay? So we can say that import negatively correlated with positive the export. You see, the import negatively correlated with the export in this angle, and it's at what? Negative 22%. It's negative 22%. So it might be that elasticity, it can be that it's a percentage change. I don't want to go to the regression aspect. The percentage change will lead to this, but this what you are talking about. The relationship between the import and export is negative here. Okay, it's negative here. This is a raw data. This is a raw data. So we can actually situate our explanation in this angle. When we're talking about the correlation here, we said that this net export import here correlate to export at this, because this was total raw data. Nothing, no EGON component, no other variable happened. Why is it like this? Why is it like this? Then when we perform the PCA, we realize that yes, the problem is this, which means that it actually affects export. The relationship between import and export is negative. Are we okay?
Yeah, thank you very much. No.
Okay, all right. That's a layman term. But the statisticians are here. Yeah, Mr. Molly, please, your hand is up. You can come.
Thank you. Yes, when we were plotting the loading plot, when we are doing the loading plot, based on the value we had from the principal component analysis. For y-axis, you made us choose component 1, and the x-axis made us choose the component 2. If we reverse, what is any rationale behind the y-axis being component 1? Is it because of the 8 interval is the highest, or there's no rationale for we choosing any of them we choose? We will be able to get that.
Any of them is okay. You just want to check. You just want to check the loading plot. You just want to check the loading plot.
Okay. So assuming that we had 3 values, but if the values for the aging value that are more than 1, if they were to be 3 or 4, how are you going to do it?
So we only have x and y axis. You just plot 2, and then later we plot another one against another one.
Please, I didn't get you.
The axes are only 2, right? Right. So we plot the 2, first and second. You plot the second one against the third one against the fourth one against. You can just plot it side by side.
Okay, thank you.
All right. Yeah. So the most important here, the PCA that we calculated here. That's the most important thing we are talking about here. And anyway, you can also go ahead to do another post estimation of prediction, residual, etc. Okay, you can also go ahead to do it, but we are not interested in that. Okay. Now let's go to the last time Mr. Johnson was talking. Also talked about the logarithm aspect. Now I want us to take a closer look at the variable, the data here. Go to the data view. When we go to the data view here. Now you see that our data is actually okay here. But we have some, let's make the data perfect by dropping let's make the data perfect. There's too many zeros in it. So we say drop if TFP is equal to 0. Now, so we don't have any missing. The this thing is perfect here now. So we are okay. But when you check our analysis, our data, you realize that you see GDP growth, they are negative in it. Okay. And then net export, there's also negative here. Okay. Now, if you want to transform this to a natural log, to logarithm, right? Let's try to transform, say generate. To form a logarithm, you have to generate. Let's say lane. We are renaming, we are generating, we are generating another variable in the stata. We are generating another variable, or in our data view, we are generating another, we are naming it. Okay, renaming another thing to make it perfect. Let's say the first one was what? GDP growth. So let's name it GDP underscore G, right? Right? Equals to log of a bracket of the variable we are generating the log for. Log of. Now, and then you close the bracket. Now, and then you click enter. But you see, when you generate it, we have 3 missing value. 3 missing value. You ask, why is it that there are 3 missing value? Mathematically, when you generate a negative log, it becomes what? Okay, let me go to a statistician. Mr. Johnson. Yes, Mr. Johnson. Statisticians are there. Mr. Johnson, tell us, can we transform a negative to a natural log or whatever?
Oh, thank you, Doc. I would like you to go on. I would like you to go on, please. Thank you.
Now, okay. So you see, when we have negative, we cannot, when you the negative of something is logarithm of a negative of something is 0, right? So in stata, when we transform a data which is negative signed, right, it becomes missing. It's become omitted. It becomes 0. It becomes nothing. It doesn't work. Okay, it doesn't work. So how do we correct this? Because we want everything to be, all the figures, all the variable, all the data should be set. Now, since we have that, we can just drop it. Let's drop it. This is how we drop. Drop. Just drop this one, call it back, you enter. It's out. It's no more there. Now, then we go back to the data, the data in the system. The GDP growth side, we have, okay, -3, -6, -4. Then we go down. There is nothing there. There is nothing here. So the highest value here is -6. So what do? We remove the -6. How do we remove the -6? We come back to the command phase there. We command a phase here. Now, then we regenerate another variable. So we say GN. So let's rename it. GN let's GDP underscore G. Okay, underscore G. Now, if we say GDP underscore G equals to the GDP here, this one. Now, what is the highest negative value over there? -6. So we say plus 6. We add 6 to it. Then when you enter, it's corrected. Let's go back to see whether it's actually corrected. Yes. So you see, here, it's corrected, but we still have negative here. GDP G, we have negative here. Now, then what happened? Why do we have negative here? Then let's look through the data again. You see, when we look through the data, we say it's -6. So when we add -6 to this, then the negative is still there. Then what do you do? So it means that here, we should not have add negative. Instead, we should have add plus what? 7. So, okay, it's already, so we drop it. We drop it. Let's drop it and redo. Now it's now dropped. So let's regenerate. So we regenerate GDP underscore G equals to GDP underscore growth plus 7. We enter. Now let's go back to our data again and see. Back to the data, we now see that everything is accurate. Everything is accurate. Now, since everything is accurate, let's now go back to transform this to the natural log, to transform it again. We say generate again. Lane. I already have it here. So I call it, but since, yeah, I call it. So I'll now call this one back into it. Link GDP underscore D equals to log of a bracket of GDP underscore G. Then you enter. When you enter, you see, we no longer have missing values here. We no longer have missing value here. So this is how you transform the data to the logarithm form. But you see, when you also go back to the data, you see net export also have negative. There's negative here. There's negative here. So we also have to need to correct this before we transform the data. So let's see, Madam Maureen, how do we transform this, the net export? Tell us the command so that we carry on. From the data, we have this. And the highest here is -25.
I wanted to ask a question why we added 7. So you're coming in with another one. So I think we will add 26.
Okay, you wanted to ask why we add 7. Now I ask you. Now you are saying we should add. No, we should add 26. No, why are we adding 26?
That is the question I wanted to ask.
Okay, so basic mathematics back in the primary school, elementary school, they say that if you are borrowing, if you owe 2 and they give you 2, what do you have? 0. But if you owe 2 and you come to pay 3, you have extra 1, right? So you don't have negative again. So the reason why we add -7 is to take off the negative sign. So negative plus positive. The higher positive, the result the final answer, the highest number, right? The sign attached to the higher number affect the final answer. Hey, I remember. I remember from my. Yeah, I've tried. Mr. Molly, I've tried, right?
Perfect.
My primary school.
Yeah, primary school. Perfect.
Yes. So, ladies and gentlemen, this is how we generate, we transform the data. We transform it to this angle. Now, so the same way we can generate the log, we can transform this same data, which is the net export. So generate by adding, right? Generate its net export. So we can say X P underscore P, right? Equals to net export plus 26. So we see, if we were to generate it, we were to transform it to log, we'll have a missing value of 265. No. Oh, sorry. I add 265. Let me drop it. All right, so let's regenerate. Okay. Now, I'm sure if you transform it to the logarithm form, ln xp exp, right, equal to log of this. Please put in a bracket. All right, so we have it here. So you can see when you come back to our data here, you see the net export, which is this one, doesn't have a negative sign again, right? And then when we generate it to transform it to the natural log, we have a sizable number here. So it is important we work on our data. It's also a way of polishing the data. It's also a way of polishing the data. Now let's go to, today we want to do some diagnostics. Hey, how time flies when you're having fun. Now, let's do a simple regression analysis and check some of the diagnostics. So, general regression, let's do any question before we do the regression analysis? All right, silence means consent. So let's do
I have
this.
a question.
Please, you can ask, sir.
Yes, please. When we log transform GDP, we are having some negative outcome. Doesn't matter.
Really?
Yes. I don't know whether it's
The log of
log GDP, the third value, or it's not.
Yeah, we are negative 2 point.
Yes.
I think we also have on net export.
Net
I
export.
can see
All right. Kashigbe, don't worry.
Okay. Fine.
But we don't have any missing variable here. It's perfect. It's correct. It's perfect. It's correct. We cannot, if you want to transform that again, we need to correct that negative sign.
Okay.
It's correct.
No problem.
There's no problem. So we perform a regression analysis.
Hello, Doc.
Sir, please come in.
So when you were to change the GDP to the lane, you enter lane GDP underscore G and export to that's the ESP underscore P. So how do you know, or when do we use those acronyms, like either the P or the G, especially if I'm to do for health? What will I use?
Okay, that's a very good question. That's a very good question. You can choose. You can use anything. There is no root. There's no. I am just renaming the variable the way I want to name it.
Okay.
There's no rule of thumb anywhere. You want to name the variable the way you want to name
it. Okay. All right.
There's no theory. There's nothing attached to it. All right.
The last one, when you are trying to drop the negatives, you added, for instance, the export, you added 26, and that of the GDP, you added 7. And so in this case, is it that you look at the highest negative? If the highest negative is 7, that's when you add 7, or it should be plus 1?
Yes. Plus 1 of the highest.
Okay. So that means negative 6 should be plus 7.
Plus 7.
Okay, though. Thank you.
You're welcome. Can we continue? All right. So the regression analysis, let's perform it. So the basic one is REG, right? REG. First of all, the dependent variable will come first before the explanatory variable. In regression analysis, REG, the dependent variable before the explanatory variable. So here we are taking TFP as, so you can type TFP, right? Or basically you can just come here. You can double click, or you see when you have here, there's arrow pointing, you can just click the arrow, it will come. Especially those of us that our hand typings are fast, and then we realize that we have a command not there, variable not defined, and all those things. Those of us that our hands are fast, we can tap and tap. To avoid that, ladies and gentlemen, just go back, go to the variable. Either you double click or you click the arrow. Double click or you click the arrow. Okay, now. So we have TFP. Let's regress GDP growth, export, import, okay, and then let's just do these 3 independent variables. Now, perfectly as it is. Now, when you look at this result, you can see a lot of things happening here. We have the model, the residual, total, SS, DF, MS, that we talked about in the previous lecture. And before I started the lecture too, I also talked about this. I saw mean square error. I also talked about this before we started doing the tutorial. I also talked about the adjusted R square, and then the R square, we talked about it. Now, in the previous lecture, we talked about it. Let's now come to this place. One of the mistakes that most people do is that, you see, let's talk about the T value here. The T values here. Now, first of all, to know that the data is the model or is significant, First of all, you can check here whether the entire model you estimated, the entire model, you see from here, the entire model you estimated, the justification of the entire model depends also here. Now, the model is significant at this level. The entire model is significant at this level. There's no ambiguity in the model. There's no specified model here. The model here is not specified. Sometimes you run an analysis and you see that the probability F, which is the P, is a 0.999, so it's already, there's a problem there. First of all, let's check this place too. I'm much particular about this. Let's check it. Before we come to the R square, the adjusted R square, let's check this. Now, you see that GDP growth impacting TFP is not significant because it's above the threshold. It's really above the 95% confidence interval that we are assuming, and that we are accepted, that we have taken, right? It's above, it is more than, it's more than 5%. This is 16%. So GDP growth affecting TFP, though it is 0.01, that is the how GDP growth explains TFP. It is not significant. But it doesn't mean that the model we should not accept. Yeah, we can write to support that, yes, GDP growth affected this, but it's not significant. Now, when we come to export affect TFP at 0.03, right? 0.003. And it's significant because of this p-value here. This p-value here. And then this is also significant, which is already negative. You see, theory support, when you check theory and literature, they don't lie sometimes. Sometimes they lie. This is actually true. It's possible. It is possible in a country or nation that actually depend highly on import. They are always having a deficit in their balance of payments because you buy more, you sell more. So what do? You have deficit. So this is also one of them. You can see it here. Now, the constants. Sometimes people ignore the constants. People ignore the constant. You see, when you write a model, write an equation, right? You say TFP equals to. I want to see if I can write this model. Good. Please bear with me today. I will take a little time small. Let's want us to wrap up something here.
More time.
All right. So I want to set a model here and see. Let's set this model and let's set this model here. We say normally, let me use the information that we have. TFP equals to, let's say, baseline TFP equals to
3.43.
Say again.
Okay, I thought you had 3.4380. 3.438404.
I want to set the baseline estimation equation first. It's good. It's good that we have statisticians you have econometricians in the class. So we have the variables are, let's say, GDP underscore growth plus export plus import, okay, plus import, okay, plus the error term of say, all right, it's a baseline. So we estimate the equation by saying that, this is the equation. But if you want to set it as a model equation, we say that TFP at a particular time interval plus a constant say alpha equals to a constant alpha plus a coefficient variable beta of GDP underscore growth plus a coefficient factor beta of export plus another coefficient factor beta of import, then plus the stochastic, plus the disturbance term or the error term. Now, plus the error term. Now, you can see from this angle here that a constant start with 0, not. A constant is not. And then we have the first coefficient of beta 1, second coefficient of beta 2. Sorry. And then third coefficient of beta 3. All at a particular time frame at time t. And then the error term is also at time t. Sorry, I'm taking your time. Sorry. Now, please, have you seen this? Now, you see this equation, this model I've specified here. I'll specify this model here. Now, the constant here, this is the constant here. This constant, the alpha variable is this constant. No, the question is, but is the constant actually significant? Holding other things equal. Is holding things equal significant in a way? Now, I'm sure you can see the two, the table, the Word document, and then the STATA as well.
Yes, please.
Okay. Now, you see the constant here, the alpha naught. This is the constant, this one. Basically, we ask, is he actually significant? But sometimes, let me tell you this secret. People think that if the constant is not significant, it's okay. But you are setting your hypothesis based on the assumption that holding all other factors constant. The factors you are holding constant, are they actually significant? Are they important before you are holding them? We overlook that, if this is not significant, it doesn't matter. But when you try to estimate all, you should not forget that the constant is part of the equation. The constant is part of the equation you have set here. So we also have to take into consideration the significant level of the constant. And make sure when you are writing your papers, you are writing it, make sure you include your constant into your write-up and then justify it properly. That the equation is set like this, holding other things constant. The other thing constant are the stochastic that might not happen or that might happen. But yes, you hold them constant because they are significant. And your analysis also prove that it's significant. Okay, so, and then you see the equation here, 0.001 is this beta 1. And then 0.003 is this beta 2. And then negative 0.001 is this beta 3. Now, the error term, the stochastic, is this we are seeing here. The residuals is the error term. So it's very important when you run your analysis, you check if your model actually is fit for a purpose. If your model is actually fit for a purpose. Now, we talk about performing some diagnostics. And the diagnosis, I say you can perform VRF. You don't need to do any other thing. Just type VRF. And then you click it. Now, let's look at this whole thing. Let's look at this whole thing. Now, the VRF, the rule of thumb said that if it's less than 5, then there's no problem. The model is actually fit for a purpose. If it's exactly 5, so this is 5%, this is 5%. So the model is fit for a purpose. One of the diagnoses we are talking about is that if the mean VRF is 5.0, if it's exactly 5, less than 5, it is okay. So now the general model is what we are talking about. We are not talking about the individual here. We are talking about the general VRF here, the mean VRF. So when you run your analysis, as I said in the beginning, when you run your analysis, you need to perform the VRF. Let me take you back to the slide here. Yes, the VRF here, the slide I spoke about here. This is a very good fit. It is less than, it is in the range from, let me take you to the rule of thumb in it. Yes. Now, checking the rule of thumb. The rule of thumb here. It said that VRF, when it's like this, no problem. When it's between 5 to 10, there's a moderate concern. But above 10, there's a serious problem. And you see that our analysis prove here, our VRF proved 4.87, which means there is no problem of multicollinearity in the result. It means that the model is actually fit. So every decision we take, every suggestion, every analysis, every pronouncement we make based on this analysis, it is fit for a purpose because of the VRF. Somebody will ask those who join late, what is VRF? The VRF is a variance inflation factor. It's a statistical measure used in regression analysis to dictate if there's multicollinearity. That is, whether independent variables are highly correlated with each other. Okay, That is if they are highly correlated with each other. Now, we said that if the R square is high, then the VF becomes large. Then we have multicollinearity problem. But if the R square is not high, the high here I'm talking about, you are having from 90%, 90 above, the VIF will definitely be large. Then there will be a problem. But when it come back to our analysis here, our R square is 64%, and adjusted is 61%. So that's give this result. So, ladies and gentlemen, one of the diagnoses that we should perform after running your model, after estimating your model, just go back to the system, type VIF. Then it will bring this out. But if this is large, there will be a problem. If this, there's also be a problem. Are we together?
Yes, please.
So I want us to, in a matter of understanding, get this clear. Now, there's one rule of thumb here. We can also perform another analysis, right? Analysis to check if the model is fit. We can perform the histogram. Okay, histogram of the residual. Histogram of the residual. So we can just type the command histogram of residual. I'm just picking it from my do file direct to this place to check for normality. Okay. Variable rich is not fun. Okay. I think I've called it for another. Okay. Oh, sorry, I've called a different thing. Sorry. So we'll check for that to perform the histogram and see if we have a bell shape. The example I gave us a bell shape. We can also perform the white noise for it, the W Western to check it. I'm coming, ladies and gentlemen. I'm trying to call the do file here. Any question, please? Hello.
Yes. Yes. When we run the model, when you were giving us the model, you show a particular figure as the stochastic, the residual. Is it the 0.0082?
Yes, please. It's there. It's written the residual.
Okay.
Right. My do file is corrupt. Sorry, my do file is really corrupt. I'm finished. Ladies and gentlemen, I'm finished. Come on. All right. That's a problem for myself. I'll face it myself. So please, gentlemen, perform the VRF, and then you determine whether your model is fit. It's one of the diagnostics. It's a very important thing to do. One of the very important diagnostics we have to do. Any comments? Any question?
Hello, sir.
Yes, please come.
Yeah. My question is, let's say, not really, though it's related, but a bit distant. Like, whilst dropping some of the variables, I mistakenly dropped the GDP growth. So if you want to call it back, how do you do it?
Just click it and enter.
Okay.
Sorry, my do file is corrupt. I don't know what I click and then it has taken all my do file away. That's taken all my do file away. All right. Any other question? Now, sometimes you can also perform the Bruce Pagan analysis to check, as a diagnostics, that you check for test for heteroscedasticity in the data. And you see, when I call the heteroscedasticity, that one work. When I call it, the command is HETTEST. Please type it in the command base and then hit enter. Do you have it? All right, so we can perform. Please, my file is corrupted, so we can perform 3 of the diagnostics tests to check if our model fits. The Bruce Pagan, the VAF, and then with Frederick analysis to check of our model fitness. When we perform the VI vector inflation factor, we realize that the mean VIF is good, so the model is fit. When we also perform the Bruce Pagan, the probability chi-square is also good, which is what 0.3, which is quite good for us to say that there's no constant variance, the variable fitted value of this, so it is quite also okay. When we perform the Bruce Pagan too, we also have it here as well. And then the Bruce Godfrey LM test for autocorrelation, we also realize that our p-value here sound well. It's very, very good. Our p-value is very, very good. So it's okay here for us to accept that our model is fit for a purpose. Our model is really fit for a purpose. Any question, contribution before we bring the class to an end? Madam Maureen, Madam Joan. Hello, sir. Madam Joan.
Yes, sir.
Are you in the class?
Yes, please.
We did not see your voice today. We did not see your voice.
Yes, sir. Because if people are confused.
You are confused?
It's quite technical. So I'm listening. I'm paying close attention.
Wow. I'm sorry. We
Oh, no. I'm just I'm learning.
Okay. I myself, I realize that today I'm going fast. I don't know why. Don't worry. We are together. Mr. Collins.
Yeah.
Any issue?
I think I'm paying close attention. I'm learning something new. So.
Okay. What about Mr. Frank? Mr. Frank?
Yes, I was.
Any issue? Are you in the class?
Yes, I'm in the class. I'm following. There's no issue.
You are following?
Yes, sir.
Okay. Madam Linda? It's you. It's you.
Yes, sir.
But
I'm here.
Are you sure?
Yes.
What about Madam Sharon? Madam Sharon, are you here? Oh, Sharon, why are you laughing? Because you know I'm coming to call you, you are laughing. For me to know that you're in the class. Sharon, are you in the class? Okay.
Yes, please, I'm here.
Are you sure you're here? you just log on. All right. Okay, Mr. Johnson, anything to add?
I have. Before Mr. Johnson come in, I want the clarification. When you look at the Godfrey or whatever, the autocorrelation, that kind of thing, the both text. The heteros test. You saw you saw the chi-square and you said that is okay. What is the rule of thumb for that? It's 0.39.
So 0.39.
Yes.
So what's the sign like? What sign is this? Less than, greater than.
Yeah, you see the probability is greater than the greater than the chi-square.
So less that means than, greater. Yeah, it's okay.
Okay.
You see, I remember those times in school, we say less than, greater than, equals to.
Okay, thank you.
You guys are making me bring my elementary. Less than, greater than, equal to, addition, subtraction, multiplication.
Your teacher was a
Well, he liked me as too much. All right, Mr. Johnson, anything to add before I go to Madam Gertrude?
Doc, thank you for your time. I think to also add to what is it, Mr. Mowley just request. If you look at the interface, you see that the hypothesis has been stated.
Yes.
H not constant variance.
You
see, so most often once the p-value with this test, once the p-values are greater than the five or 5%, it means that there's no H2 in the data, but there's homogeneity of variance. So sometimes we can also pay attention to such as well. Thank you.
So again, please, you pay a close attention to the top. When you run your analysis, pay a close attention to the top here. It's also important. Most people only pay attention to just here and go. But most attention, you see, the fitness of the entire model depends here. Depends here. 1, 2, 3 here. 1, 2 here. The fitness of the entire model depends here. So when you submit the paper to time series journal, they will ask you to report everything. Like this thing, they will ask you to report it in appendix, but write it in a word, report it in appendix. Because they may not have the data, right? They may not have the data. They might not require for the data, but you can use this place to recheck your work for you. But it doesn't mean which means that you should be careful what you put here. Okay, it should be don't go and cook it. If you cook it, it will not be well cooked. You have to add water, it still not be well cooked. So put it raw like that, is cooked like Madam Gertrude, and then Madam Irene. Final comment from the two of you. Madam Gertrude is in the class even. Then I'll go to my president in JUA. Madam Gertrude. Okay, today, Mr. Isaka. Is that a name?
Isaka.
Mr. Isaka?
Yes,
Isahak.
yes, that's the name. Yes. I'm
Uh-huh.
following.
You're following? Good.
Yeah. Just that I've not been able to follow with the operations. I will later watch the video, and then I had issues with my laptop.
Okay. That's okay. Mr. God bless. Oh, Dr. God bless. Anything to add? I said, no, Mr. God bless is not in the class. But Dr. God bless is on the line. Ladies and gentlemen, I have this assignment to give to us so that next Monday when we meet, we'll perform it. Please write this down. Run a regression with TFP as dependent variable and use the transform log of GDP growth, export, net export, and then education. Transform the logarithm of GDP growth, export, net export, education, and import. Please, when we meet, I'll randomly call somebody to give us the results of his analysis.
Please say a question again. Repeat it.
Run a regression analysis, multiple regression analysis with TFP as dependent and then GDP growth as independent, exports as independent, import as independent, net export as independent, and education as independent. And then the second one, the same thing, but the independent should be the logarithm form. Transform all those independent variables to perform the analysis with. So we now have lean GDP growth plus lean export plus lean import plus lean net export plus lean education. Thank you, ladies and gentlemen. And then do the model diagnostics, let's see. So the diagnostics aspect, perform the VIF for all. Just perform the VIF for all. For the two multiple regression, the two equations, perform the VIF for all.
Please, Doctor, if possible, you can send for us to the group the questions. Today you are so fast.
Yeah. That's why I say that. That's why I say, hey, that's why you see. Today I'm so fast. I promise not to be fast again.
I even wanted to write, but I couldn't.
I thought it was
me. Hey, today. Okay.
Today you are running.
Yeah, you say what?
I'm sorry. Next time we'll take it step by step. All right. Thank you
Yeah,
very
it's part
much.
of it.
Thank you very much. Thank you very much. Thank you very much. So, okay. So, ladies and gentlemen, please have a good evening. Those who are joining the other class, you have about 30 minutes to join the other class. Do have a nice evening and enjoy the rest of your evening as well.
Likewise.
You too. Thank you.
You too.
You're welcome.
Thank you so much.
God bless
Bye
you.
bye. Joanne, because you did not answer a question, you are clapping for me. Don't worry. I will send you a message backstage. Joanne, I will get you. All right. Bye-bye.
Bye.
Mr. God bless. Or whoever is doing the recording can end the record now. Okay. Madam Marie. Mr. God bless.
Hello, Doc.
Hey, I miss you. I called you in the class. I called you in the class.
Oh, really? I was working on the other platform for the meeting, our class. So I just
The one recording
that arrangement.
The recording now.
Oh, okay. I think let me check. Dr. God bless is the one doing the recording. I think he's away from the machine. So since you are the host, once you end the meeting, automatically the recording will convert for upload.
So I can end the meeting here now.
Yes, I think it will work.
Okay.
All right. So we'll meet later. Thank you so much for your time.
You're welcome. You're welcome.